Rotational motion. Objects rotate around a fixed point. In the previous chapter, we did linear motion, in which objects are able to travel in the x, y, or z direction. This is called translational motion. When we have rotational motions, objects rotate around a fixed point. In linear motion, we had objects go from a point A to a point B. We stated that this was the object's displacement. Which is also known as delta x, which is the final, here in this case, point B minus point. In the vertical direction, we use delta y, or h, and the SI units for linear, remember, was meters. Similar to displacement in linear velocity, in rotational motion, we call it angular position. This angular position is theta. Theta is from one point to another point along the circle. So for example, we could select a reference point and label that theta naught, my initial theta. As the object travels in a rotational motion, its angular position changes to a final theta. To find the resultant theta, that's delta theta, which is theta final minus theta initial. This is measured in radians. Radians is the SI units. So what is a radian? In math, it is defined as when the arc length is equal to the radius. Another way we could define theta, or angular position, is the arc length, which is this outer part that the theta traveled, over the radius, which is the distance from the center to the outer edge of the circle. We could rewrite this formula as arc length as S over R for radius. In math class, if I take the circle and divide it into 4 quadrants, you guys know that this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees, and it comes back to 360 degrees. So to complete one revolution means I start at 0 and I complete one circle and get to 360 is equal to 360 degrees. You also know that in math that, again, if I draw this into quadrants, if this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and so this is 2 pi. So that tells you that also one revolution is equal to 2 pi. And since we're in radian modes, the unit is radians. If this is true, we also can say, since these are both one revolution, 360 degrees is equal to 2 pi radians. Or if you reduce this out, it becomes 180 degrees is equal to pi radians. So you need to memorize 1 revolution is equal to 360 degrees. 1 rev or revolution is equal to 2 pi radians. And 180 degrees is equal to pi radians. If you notice, all 3 of these are equal to each other. So if you want, you could just memorize 1 rev is equal to 360 degrees, which is equal to 2 pi radians. In order for an object to go from point A to B, the object must have velocity. Velocity was defined in change in displacement over change in time. And so we could rewrite that as v is equal to delta x over delta t. And the SI units were delta x was meters, delta t was seconds, so the units were meters per second. To move from point A to point B, an object needs a velocity. This velocity is known as angular velocity. Angular velocity is the change in angular position over change in time, which can be rewritten as angular velocity symbol is omega, small Greek letter omega, equal to change in position we define as theta, so it's delta theta, over change in time is delta t. So this will be theta final minus theta initial over change in time. The SI units for theta is radians. So this is going to be radians per unit of time, which is seconds. So as the object goes from point A to point B, it's going to have an angular velocity. So we know velocity is a vector. In linear velocity, we just write the correct direction as north, south, east, west, or we find the angle using tangent theta and given direction. For rotational motion, we must use the right-hand rule. Curls of the finger is along the rotation. Thumb is the direction of the angular velocity. So the object is rotating counterclockwise. My curls of my finger goes around the rotation. My thumb points up. So that is the direction of my omega. Vectors cannot curl. So the omega is along the plane of the axis of rotation. In linear motion, we said objects can speed up or slow down. When they speed up or slow down, they have acceleration. We defined acceleration as the change in velocity over the change in time, which is rewritten as A for acceleration equals to change in V over change in T, which is V final minus V initial over T final minus t initial. We know the SI unit for velocity is meters per second, and the SI unit for time is seconds. So the units for acceleration is meters per second, or meters per second squared. When objects are speeding up, the acceleration and velocity must be in the same direction. So if the acceleration is in the negative direction, then the velocity must also be in the negative direction. If the acceleration is in the positive direction, then the velocity must be in the positive direction. Objects could also slow down. When they're slowing down, the acceleration and velocity must be in the opposite direction. So if acceleration is in the negative direction, velocity must be in the positive direction. If the acceleration is in the positive direction, then the velocity must be in the negative direction. Similar to linear acceleration, which objects could speed up or slow down, objects that are rotating can also speed up or slow down using angular acceleration. Angular acceleration symbol is alpha, the Greek letter alpha. Just like acceleration is defined as change in velocity over change in time, angular acceleration is defined as change in angular velocity because it's rotating around a fixed point over change in time. Remember, angular velocity is omega, so it's delta omega over delta t, which could be expanded out as omega final minus omega initial over t final minus t initial. The units for omega was radians per second over time, which is another second. So it's radian per second squared. So if object starts at point A and moves to point B in the counterclockwise direction, if it speeds up, its angular velocity and its acceleration are in the same direction, just like in linear acceleration. If it's slowing down, the angular velocity and my angular acceleration are in the opposite direction. So you could kind of think of it as it's braking. So similar to linear, when it's speeding up, my alpha angular acceleration and my angular velocity are in the same direction. So they could be alpha positive, omega positive, or alpha negative and omega negative. If it's slowing down, alpha and omega must be in opposite direction, similar to linear acceleration. And so if alpha is negative direction, then omega must be in the positive direction and vice versa. To find the direction of the angular acceleration, we use the right-hand rule, just like for angular velocity. Remember, the curls of the fingers represent the direction of the rotation of the object, and the thumb points in the direction of the angular velocity. Let's look at the first picture on the left. If I look at my left, my object is rotating counterclockwise. So my finger goes counterclockwise. My thumb points up. So the direction of the angular velocity is up in the direction of the plane. Remember, vectors cannot curve, so the angular velocity is in the same direction as the rotation of the axis. If the object is speeding up, the angular velocity and the angular acceleration must be in the same direction. So the direction of alpha, or angular acceleration, will also be in the same direction if it's speeding up. So in the second picture, we also know that the angular velocity is pointing up because the object is rotating counterclockwise, so that's where the curls of my fingers are, and my thumb points straight up. So that is the direction of my angular velocity. So if it's slowing down, my angular acceleration must be in the opposite direction. So when we find the direction of angular velocity and angular acceleration, always use the right-hand rule. First, you find the direction of the omega, or angular velocity, and determine if the object is speeding up or slowing down. If it's speeding up, the angular velocity and acceleration are in the same direction. If they're slowing down, angular velocity and angular acceleration are in the opposite direction. When an object moves along a circular path, its instantaneous linear speed is known as tangential velocity. So if we have an object that is traveling clockwise, tangent to its path is my tangential velocity. If the object is down here, its tangential velocity again is tangent to its path. And same goes up here. We know that velocity is defined as displacement over time. That displacement is the arc length, which is S over T. We know that S, the arc length, is also R, the radius, times theta, the angular displacement, over T. Theta over T is omega, angular velocity. So V tangential can be defined as radius times omega, in which omega is in radians per second, R is in meters, and velocity tangential is meters per second. So if we have two objects that start at theta naught, object A and object B, it travels along the circle and ends up at theta final. The angular path traveled by A is this right here, this distance. The angular path traveled by B is this distance. To find the angular position, theta, we know that it is theta final minus theta initial. Since both A and B started at theta initial and both ended up at theta final, their theta, change in theta, is the same. This signifies that no matter where A and B is from the center of the axis, if they cover the same angular position, delta theta, their angular velocity will be the same. So V tangential is equal to R omega. Omega is constant because delta theta is the same. So if we look at A and B from the axis of rotation, radius of A is much smaller than the radius of B. Because B is further away from the center of rotation, it is going to have a greater angular velocity. So R increases, V tangential increases because V tangential is proportional to the radius and vice versa. This alpha sign here is proportional to and not angular acceleration. When objects move along a non-uniform circular motion, it has a tangential velocity. So object up here will have a path that's tangential, and that is my tangential velocity. Since the object is moving in a non-uniform circular motion, its velocity is changing. Therefore, it is accelerating. It might speed up or it might slow down. This acceleration is known as tangential acceleration. This tangential acceleration is due to the angular acceleration. Acceleration was defined as change in velocity over change in time. In the previous slide, we learned that velocity tangential was equal to R times the angular velocity. So substituting this in, this is V final minus V initial over delta t, which I substitute in for the velocity. So this is R omega final minus R omega initial over delta t. We could remove an R, factor out an R, so it becomes omega final minus omega initial over delta t. Change in omega over change in t is alpha, or angular velocity. So we could substitute in for delta omega over delta t. So this becomes R times alpha, in which R is in meters, alpha is in radians per second squared. So acceleration tangential is meters per second squared. tangential acceleration is the radius times the angular acceleration. Since tangential acceleration is a linear acceleration, the direction will depend on if it's speeding up or slowing down. If it's speeding up, then as before, V and A will be in the same direction. If it's slowing down, it will be in the opposite direction. Speeding up, my acceleration will be in the same direction as my tangential velocity. Since it's moving in a circular motion, it has centripetal acceleration. Centripetal acceleration is defined as center seeking. It is equal to velocity squared over the radius. This velocity here is the tangential velocity. So we said V tangential in the previous slide was R times omega, which is the radius times angular velocity. Substituting in, I'm going to square that over R. This becomes R squared omega squared over R. One of the R's cancel out. So AC, or centripetal acceleration, becomes R, the radius, times the angular velocity squared. Remember, SI units for angular velocity was radians per second. Since there's two of them, this is going to be radians second squared, and the radius is in meters. Units become we have centripetal acceleration because the tangential velocity is changing and there's a centripetal force present. The direction of the centripetal acceleration is always towards the center of the circle. So this is AC. If this object is speeding up, its tangential acceleration will be in the same direction as the tangential velocity. At this moment, or instantaneously, the tangential acceleration and the centripetal acceleration will be perpendicular to each other. So to find the resultant acceleration, you must use Pythagorean theorem. So my AT is going across. My AC is toward the center. If I draw the parallelogram method, I take the AT and shift it down, same magnitude and direction. AC shifted over, same magnitude and direction. The resultant starts from the tails to the tip, and this is the A total. So A is going to be Pythagorean theorem, so AT squared plus AC squared. Take the square root, and we could find the angle using tangent theta, which is opposite over adjacent. And opposite, if I choose this angle right here as my theta, that will be AC, centripetal acceleration, over tangential acceleration. So in rotational motion, there are two types of acceleration. Tangential acceleration, which is radius times angular acceleration, and centripetal acceleration, which is radius times angular velocity squared. To find the net acceleration, we need to use Pythagorean theorem and solve the direction using tangent theta. Also note, the reason we get to use Pythagorean theorem and tangent theta is in that instant, AC, centripetal acceleration, will be perpendicular to AT, the tangential acceleration. Tangential acceleration will change because of changing speed, and centripetal acceleration will change because changing direction. Remember, acceleration is a vector. So if the direction changes, even though the amount is the same, the magnitude, the acceleration will still change. Since we've been comparing linear to rotational, linear kinematics will also become rotational kinematics. X, or distance, will become theta, angular position. Velocity will become angular velocity, omega, and acceleration will become angular acceleration. So the formulas are the same, except for x is swapped with theta, velocity is swapped with omega, a is swapped with alpha. Problem is number 12 in your textbook. A 70 diameter wheel accelerates uniformly about its center from 130 RPMs to 280 RPMs in 4 seconds. RPM is angular. So that's omega naught. That's 130 RPMs. It went from 130 to 280, so that's omega, or angular velocity final, RPM. And my time is 4 seconds. And I am looking for angular acceleration. The only rotational kinematics with this equation is omega final equals to omega initial plus alpha time. First thing I need to do is convert. These are in RPMs. This is in seconds. So using my conversion factor, remember we said 1 rev is equal to 2 pi rads, or 360. We're going to convert it into the SI units of radians per second. So I have 130 RPMs. This is revs per minute. 1 rev has 2 pi radians. 1 minute has 60 seconds. This is my initial. My final, we're going to do the same thing, RPM, so it's going to be revs per minute, 2 pi rads, 1 revolution, 1 minute, 60 seconds. So this becomes approximately 13.6 rads per second. This becomes 29.3 rads per second. So now I'm going to plug that in. So this becomes 29.3 rads per second equals to 13.6 rads per second plus alpha times 4 seconds. Solve it and you get approximately 3.93 rads per second squared. So in part 2, we're finding the radial and tangential components of the linear acceleration at the edge at 2 seconds later. So in order to do that, it depends on omega. So what we need to do is find the final omega at 2 seconds. So using the same equation, omega final equals omega initial plus alpha t, we're going to find the final omega. So we're going to look for omega final. This is going to equal to 13.6 rads because that is what we started with. Acceleration is 3.93 because it accelerates uniformly about the center. And we know the time is 2 seconds. Plug this in, you should get approximately 21.5 rads per second for part B. This is my final angular velocity. So they want the tangential and the radial. Another word for radial is centripetal acceleration. So centripetal acceleration, which is AR, same thing, is equal to omega squared times R. What is my omega? 21.5 rads per second squared. My radius is given as a diameter, so that's going to be 70 meters divided by 2. Plug that in, you should get around 160 meters per second squared. Tangential acceleration is equal to radius times angular acceleration. Radius was given as 70 centimeters, the diameter, divide by 2 times 3.93 radians per second square. Since it's accelerating uniformly, the angular acceleration is constant. Multiplying the numbers out, you should get 1.38 meters per second squared. This problem is number 20 in your textbook. Small wheel has a radius of 2 centimeters and accelerates at a rate of 7.2 rads per second and is contact with the pottery wheel, which has a radius of 25 without slipping. Since there is no slipping, the tangential acceleration has to be the same for the large and the small wheel. We said the tangential acceleration, AT, is equal to R, the radius, times angular acceleration. So substituting in, this becomes R alpha large, which is equal to R alpha small. So the pottery wheel has a radius of 25 centimeters. My alpha for the pottery wheel is what we're looking for. This is equal to the radius of the small wheel, which is 2 centimeters. And the small wheel rotates at 7.2 rads per second square. In general, you need to convert units, but here, if you notice, the centimeters cancel out. So if you convert it, it's going to be reconverted back. Solving this, alpha of the pottery wheel becomes 0.58 rads per second squared. In part B, we're finding the time it takes for the pottery wheel to reach the required speed. Since it's starting at rest, we know omega final is equal to omega initial plus alpha t. This becomes 0, and we are looking for time. The omega is given in RPMs, so revs per minute. I need to convert that because the alpha is in radians per second and the time is in second. So 1 rev is equal to 2 pi radians. 1 minute is equal to 60 seconds. This is equal to the angular acceleration we solved in part A times the time. Solving for time, you should get approximately 12 seconds. So again, you need to do some practice to understand the new vocabulary, and then it's just like doing regular kinematics.